In order to estimate our population mean effectively, we're going to need our central limit theorem to hold. And our central limit theorem says, hey, if we're looking at the distribution of sample means or proportions, it's going to become approximately normal given a large enough sample size. Now, we had certain conditions for sample proportions that needed to be met in order for that distribution to become approximately normal. For means, we need slightly different sample size conditions. Typically, if we sample 30 observations or more, the distribution will become approximately normal. We also need our sample size to be less than 10% of our population. Now, these conditions aren't set in stone. So if you do have an extremely skewed distribution, sometimes you'll need to sample more than 30 observations to accomplish your central limit theorem. However, for the purposes of this class, we'll be kind of just focusing on saying, hey, we have 30 observations and it's less than 10% of the population. We're ready to rock and roll for our central limit theorem and to estimate a population mean. For our distribution of sample means, we'll recap some things that we saw with proportions. Right? If we remember, we could have some funky dunky shaped distribution. And if we sampled enough observations, so each dot is a random observation selected in our sample, and from all of those observations, we calculated a sample mean, x bar. Right? Then what we did is we plotted that mean below on a new graph, which represents sample means. Right? So that red dot represents their sample mean. We said if we repeatedly did this process over and over again, taking observations, plotting the sample mean, taking out of observations, plotting the sample mean, as long as our sample size is large enough, which in this case is at least 30 observations, what we found is the distribution of our sample means becomes approximately normal. On top of that, the center of our distribution mu equals the exact same value down below, which we denote as mu x bar. Those two values are exactly the same. Mu equals mu x bar. Those two values are exactly the same. Our standard deviation, our standard error, sigma x bar, is a function of our original distribution's standard deviation. Right? Our original distribution had a standard deviation denoted as sigma, the population standard deviation. The standard deviation of our sampling distribution, which we call a standard error, that uses our original standard deviation and how many observations we used to comprise our mean. However, we typically don't know our population standard deviation. The only way we would know that is if we had every single observation in our population. And we're going to use our sample standard deviation to estimate our population standard deviation. Or we're going to use our sample standard error to estimate our population standard error. So these are the properties associated with our central limit theorem and associated with the distribution of sample means. When we construct our hypothesis tests and confidence intervals, our goal is to estimate the center of our distribution of sample means. Because if we estimate the center of our distribution of sample means, that mean mu x bar, we've actually estimated our original population mean.